All right, everyone. In this video, we are going to try to find optimum values or extreme values, so maximums and minimum values, subject to a constraint that we are only looking at a single curve in the domain. And I'll explain what I mean here in just a quick second. This will lead the way towards something called the method of Lagrange multipliers. Now, the example that we'll be working on throughout this video is the following. Can we find a maximum and or minimum value, so an extreme value, of the function f of xy equals x squared minus y squared divided by 4 if we restrict ourselves to a given curve that is written here in blue? Now, before I get to the curve, let's just think about the function f of xy equals x squared minus y squared over 4. And this is the multivariable function that is graphed below, both a three-dimensional rendering of the graph and also a contour plot with a color gradient associated with it. Now, I should say the divided by 4 doesn't really matter here. I divided by 4 to make the picture on the left look a little nicer. I could have also just rescaled the z-axis to keep the picture within frame. But what we see here is an example of a hyperbolic paraboloid, right? So it's one of our quadratic surfaces. And it sort of looks like a Pringle, as we've seen. And although it is currently restricted to the domain given in this box, x goes from -3 to 3, y goes from -3 to 3, we know that the hyperbolic paraboloid extends forever, and it has just a single critical point in the picture, and that critical point is at the origin, and in particular, that origin point, I'll identify it both here and here on the picture, is a saddle point, so it's not a max or a min. In other words, without any additional restriction, this function f of xy has no extreme values, just one critical point that happens to be a saddle point. Before I talk about the curve, I'll briefly mention something about the contour plot, and that is just that the contour plot is shaded in the reverse of what we are usually used to. So in particular, this area where the x values are positive and the y values are close to 0, these are the largest values of f of xy on this picture. So these are larger z values, and these are smaller z values. Just a small note, because I know we have looked at contour plots where the color gradient worked in the reverse direction. I'll also mention on the picture over on the left that the x equals 3 direction is over here. So our x equals 0 is in the middle. And then as we move to the left, in this case, we're moving in the positive x direction. So the large z areas that we identified before, sort of like this part of the graph, is corresponding to this part of the graph over here. Just to give us a sense of orientation on how the contour plot is matching up to the image on the left. Okay, well, now that I mentioned that, let's turn our attention to this curve that is mentioned here. So we are asked not to find a contour plot, not to find a maximum or minimum value on the whole function, but we're asked what we can do if we restrict ourselves to the curve x minus 1 squared plus y squared equals 1. Now this is a curve in xy space. Notice it just has x's and y's in it. So this is a curve in the domain. And also notice it happens to be, for this particular curve, it happens to be a circle. We know that if it was just x squared plus y squared equals 1, this would be our unit circle. And in general, this is a circle of radius 1. And it happens to be centered at the point 1, 0. That is how this this extra -1 piece is affecting things here. So with that in mind, let's take a look and see how we can, let's take a look and see what this curve looks like in our domain space and whether this changes our answer. So again, circle radius 1, centered at the point 1, 0. Well, that center point, I'll draw it over here, is right there. The radius is 1, so it goes through the point 0, 0, and it looks roughly like this. Ah, perfect. Look at that. Beautiful. We get a circle that looks like that. On our 3D picture, I could imagine drawing the circle in the domain, but I'm also going to draw it on the function up above. And in this case, it'll look, I don't know, something like this. It'll be a little bit, sort of three-dimensional, so it'll hug the hyperbolic paraboloid shape that we've seen. But that will be the restricted domain. And I'm not looking inside the circle, I'm just looking at the points on the circle. So what does this leave us with? Well, we'll actually notice, and I think it's actually, we can see it in either picture, really. What we'll notice is that there actually is a maximum and a minimum value on this circle, if I'm only looking at the circle. And I'm going to focus on the maximum value. The maximum value is really going to correspond to this point over here. Maybe I should grab a... Let's try this color. Oh, yeah, that's very visible. So it's corresponding to this point right here. And this point is as far uphill as we can get on the circle. That corresponds in our contour plot to this point right here. And it's specifically the point 2, 0. Now, that is our maximum value. And you'll notice, of course, that if I'm able to move off the circle and just keep moving a little bit to the right, I'm going to arrive at taller points that are higher up, but that would involve leaving the circle. And if I'm restricting myself to stay on the circle, if I'm restricting myself to stay on the curve, then this point, the point 2, 0, is the tallest point on the function f of x. So that is the framework that we are developing here. How do we find our maximum value? How do I find this point 2, 0, provided that I need to stay on this circle? And more broadly, if I have a function f of x, so a three-dimensional or a multivariable function, f of x comma y, and I have a restricted domain given by a curve, how can I identify the maximum or minimum values? And so we're going to talk about this at length below. And before I scroll down below, I want to very briefly reframe this idea here, the curve x minus 1 squared plus y squared equals 1. And so to reframe this, I want to highlight this, or I want to express this as a level curve of a second function. So I can create the second function, g of xy equals x minus 1 squared plus y squared. And so this is another different multivariable function, and the curve given by x minus 1 squared plus y squared equals 1, this curve is nothing more than a contour plot, or really I should just say a contour at g of xy equals 1. All right, and so we've slightly reframed our question. How can I find a maximum and or minimum value of one function, f, if we restrict ourselves to only look at points on the level curve or the contour of a second function, g? And here we're focusing on the contour g equals 1. All right, so that is what we are up to. Let's give it a go. To begin this exploration, I want to look at the contour plots and the gradient fields for both f and g. So the picture on the left, we saw it up above. This is the contour plot of f. but I've superimposed on top of it the gradient field of f. So all these little arrows representing grad f at different points. On the right, I have the contour plot and the gradient field of g. And remember, so in this example, we had g of xy was simply equal to x minus 1 squared plus y squared. So this is a paraboloid shape that happens to be centered at the point 1, 0. So we expect our level curves to be concentric circles centered at the point 1, 0. And now we're going to notice something really cool and really interesting. If I go back to the point that I am most interested in, and this was my maximum value, the point 2, 0, I'll mark it on both of these pictures. Okay, so if I go back to the point 2, 0, and I look at those, I can identify what my gradient vector looks like at that point. And so I'm gonna draw it slightly enlarged to embellish it. At this point, whoops, at this point, this gradient vector is pointing straight to the right. It is pointing due east in my function f. And if I look over at my function g, I see the exact same thing. In other words, these two gradient vectors are pointing in the same direction. They are not necessarily the same length, but they are pointing in the same direction. And in this case, that is due east. Now, I should say the gradient vectors do not always point in the same direction, and this is evidenced at many other points in our curve. So here's a point, sort of like a, I don't know, 30 degrees around the circle or so. At that point, my grad g is pointing off to the upper right, but over here, my grad f is pointing in this direction. So they are definitely not pointing in the same direction there. At other points, you'll see they are also not pointing in the same direction, but at this maximum value, they happen to be. Now, you'll notice over here, I have a little asterisk. The asterisk is what I mean. I guess I need to clarify what I mean when I say same direction, especially when I look at the minimum value. So this is something we haven't talked about yet. And the minimum value on the circle, I will just say, is going to be somewhere around here. And there's going to be an equivalent point somewhere up here. Now, those arrows are pretty tiny, but if you look at them at those points, the arrow, the gradient vector, the arrow, I'm drawing it large to embellish it, is going to be pointing in these directions here for grad f. And for grad g, those same points, they're actually going to be pointing in the exact opposite direction, the exact opposite. So what we have here, when I say same, what I really mean is in a parallel direction, either the same or opposite. So I'll say same or opposite, but these are parallel vectors. Okay, and then this is still in contrast to, I'll draw over it in a different color just to highlight it, and then I'll honestly just erase it. This point over at the 30 degrees, where these were not pointing in the same direction and not pointing in the exact opposite direction, they were definitely skew from each other. So that is an interesting non-example in which the grad f and grad g vectors are not pointing in the same direction. So this is a feature of the extreme values in particular. The extreme values will have these gradient vectors pointing in the same direction. And so when I say these point in the same direction, another way that I can frame that is i.e. Grad f is equal to a scalar multiple of grad g. And I'm going to introduce this letter lambda to be my scalar multiple. So i.e. grad f is equal to some scalar lambda times grad g. And we could say they are, they are scalar multiples of each other. Okay. And so this gives us a possible path forward. It's almost like a critical point, right? A critical point to our function f was a point where grad f was equal to 0, comma 0. And that's no longer the case. But now I'm looking to try to identify points where grad f is equal to something else. It's equal to a lambda times the gradient of g. And so this will give us a path forward and introduce what is called the method of Lagrange multipliers. So broadly speaking, if we want to find extreme values of a function f subject to the constraint that we're looking at a specific level curve identified by a function g and a level c, we want to find points in the domain, the x comma y values, for which the gradient of f is equal to lambda times the gradient of g, where lambda is an unknown, or some arbitrary, still unknown number as a scalar constant. So we will need to solve for the points x comma y such that the gradient of f, remember, was the partial x derivative and then the partial y derivative. So we're going to need to line those up with scalar multiples of the corresponding components for grad g. In other words, we need to solve for x and y so that f sub x is equal to lambda times g sub x, f sub y is equal to lambda times g sub y. And we need to make sure that we're still looking at points on our curve, so we will need our g of xy to still equal c. You'll notice this is a system of 3 equations, and we technically have 3 unknown quantities. We have x, we have y, and though we often don't really care about it explicitly, we have lambda as well. So 3 unknowns, 3 equations. We can go ahead and try to solve this. And so for the rest of this video, I would like to explicitly work through the computations involved in solving this for the example we've given above. And our goal will be to show that the point 2, comma 0 is indeed a extreme value. So let's take a look. We have our functions from up above, x squared minus y squared over 4, and g of xy is x minus 1 squared plus y squared. Now, I'm going to need to calculate grad f and grad g because those are important components here. So grad f is going to be the partial x derivative, comma partial y derivative. So that's just going to be x over 2, comma y over 2, where the divided by 2 is coming from the fact that there was originally a divided by 4. Gradient of g, on the other hand, well, that's going to become a 2 times x minus 1, comma, and then 2y when I take those partial x and partial y derivatives. And finally, I have the expression x minus 1 squared plus y squared equals 1. That's my g of xy equals c. Oh, wait. So that is important. But I actually meant to, before I do this, let me just move this down. I meant to turn my grad f and my grad g into the system of equations we have up above. So 1, 2, and 3 equations. So equation 1 is going to be equating the first component of grad f to the first component of grad g. And so this is just going to be x over 2 equals lambda times 2 x minus 1. All right, and we'll simplify this later. For now, I'm just writing down the equations. So that is my first equation. My second equation, I'm going to equate the f sub y and the lambda g sub y. So the y derivative, or the second component in grad f is going to be y over 2 equals lambda times 2y. All right, and then our third equation is exactly the equation that we had down below. Okay, and with this, we're going to try to see if we can find solutions to this system of equations. And let me scroll down. I don't think I have anything else on this workbook, so I just have plenty of space to try to work through these. All right, now this is a system of equations, but it's not a linear system of equations, and so it is possible that we have more than one solution. In fact, we anticipate having at least 3 solutions from the picture I set up above. Like, we might not anticipate this without knowing the answer in advance, but I said in advance we had a single maximum value and we have 2 minimum values, and so we anticipate at least 3 unique solutions here. Okay, but how do we go about trying to solve these? Well, first, I'm just going to rewrite these equations, make them look a little bit nicer. I think I'm going to multiply I don't like this divided by 2 in equation 1 and equation 2. I'm going to multiply that over to the other side. And so I'm just going to end up momentarily with x equals, and now let's see, so this becomes a 4 lambda x minus 4 lambda. That's multiplying the 2 up to get a 4 lambda and then distributing that across the x minus 1. My second equation, I'm going to get y equals 4 lambda y. And in my third equation, I am going to get, I'm just going to leave that as is for now. So I'm just going to leave that x minus 1 squared plus y squared equals 1. All right, and in short, I'm going to try to solve this by tackling one equation at a time. I'm going to start with equation 1. So rewriting equation 1, I am going to get 4 lambda, so if I want x to equal 4 lambda x minus 4 lambda, let me move all of the x's to one side of the equation. So I'm going to get 4 lambda x minus x, and then let me just move this 4 lambda off to the other side, right? So I got all my x's grouped on one side of the equation. In the next step, I will go ahead and factor out this x. So I'm going to get, factor out the x, that's right. So 4 lambda minus 1 times x equals 4 lambda. And so we have an expression for x that is just in terms of lambda. We're going to get x equals 4 lambda divided by 4 lambda minus 1. All right. Great. So we have an expression for x that depends on lambda, but that doesn't quite seem to get us where we want to go. In particular, lambda is still an unknown. So unless we know what lambda is, we don't know what x is. So let's pause on the first equation and let's pivot to the second equation. Here, let's also kind of rewrite this. I'm going to move all my y's over to one side of the equation. And here, this will actually work out really nicely. I'm going to get 4 lambda y minus y equals 0. And so I can actually factor this to become 4 lambda minus 1 times y equals 0. And now this is actually an equation that I can do something with, because in order for this left-hand side to equal 0, there are 2 possibilities. We either have so if something times something else equals 0, either the first piece equals 0, so either 4 lambda minus 1 equals 0, or y equals 0. All right. And so this is going to be the key observation that will let us begin to unpack this. All right, so let's see what we can come up with here. So if y is equal to 0, that means, and now I'm going to look at equation 3. So if y equals 0, 3 gives us the expression x minus 1 squared minus 0 squared equals 1. i.e., we're just going to get x minus 1 squared equals 1. So x minus 1 is equal to plus or minus 1. And so x could be either 1 plus 1 or 1 minus 1. Okay, and with this and also this, we actually get two possible solutions to our system of equations. In other words, we get two possible extreme values. We're going to get, I'll keep moving over actually. So one solution is the solution 1 plus 1 for x, 0 for y. And the other solution is 1 minus 1 for x and 0 for y. And so the points 2, 0 and 0, 0 are possible extreme values. All right. And with that, we have actually identified what our what we saw up above was our maximum value. Scrolling back up, we have identified the point. Actually, I'll keep this picture the way it is. Let me come back up to this original picture. We have identified the point 2, 0 as one value of interest. We've also identified the point 0, 0 as another value of interest. And so we would have to come back to that to try to discern whether this is a maximum value, a minimum value, or just a point of interest, an equivalent of a critical point that's neither a max nor a min. All right. I will now scroll back down and let's tackle the other case. Let me see here. So yes, this other case, what can we do with it? Yeah, all right. So I got stuck here for a moment. I was a little concerned actually, but I think I see what's happened. I actually made a small error earlier on, so I apologize. We're too deep into the computation, but let me point to the error. Maybe you already caught it and you were watching to see if I would catch it. But let's take a look and see what we can do here. So the issue is actually in my original computation of gradient of f. Specifically, I lost this dang minus sign. This was x squared minus y squared over 4. And so that means that grad f should really have a negative out front of its y. So this is negative y over 2. Let's see how this affects things down the road. And if we're lucky, it won't affect the points that we've already identified. So in particular, this will affect equation 2 because we should have a negative sign out front. In this rewritten form, we should have a negative sign out front here. And now let's take a look and see how that affects things in this computation. So we had a negative y. That means when we added it to the other side, this should have become a positive. And then when we factored, this should have become a positive. So either 4 lambda plus 1 equals 0 or y equals 0. Okay, so lucky us, we did make this mistake earlier, but we caught it. And by the time we got to this point, we are in a decent place because all of the analysis that we've done was in the y=0 situation. So y=0, that computation led to this and led to these solutions. So I think everything that we have on the page so far is valid. All right. I should also clarify, how did I know that I made a mistake? I was a little concerned about trying to look at the expression 4 lambda minus 1 equals 0, because that's exactly what we have in our denominator here, 4 lambda minus 1. So I was a little concerned that I was going to end up with a dividing by 0 error. So I thought there might be a mistake. I went back and I found it. And with this, we can proceed. Whew. All right, lucky us. Let's take a look and see how we can proceed with this newly fixed equation. So now we want to look and see what would happen if 4 lambda plus 1 equals 0. And so in this circumstance, that means that lambda is equal to negative 1/4. Right? That's just taking that equation and solving for lambda. So if lambda equals negative 1/4, then equation 1, going back there, can be further simplified. So equation 1 gives us, and now, not going to divide by 0. I'm going to get x equals 4 lambda. So that's 4 times negative 1/4. That's negative 1 divided by, and then 4 lambda, that's again negative 1 minus 1. So this is a negative 1 divided by negative 2. And so that's just going to be x equals 1/2. So again, if equation 2 is true, we had two cases. We have fully explored one case, and now we're exploring that second case. So in equation 2 being valid, the second case gives us our x value. So x is equal to 1/2. Well, what about y? To solve for y, we've used equation 1, we've used equation 2. To solve for y, we finally have to use equation 3. To solve for y, equation 3 gives us. And now let's take a look. We've got x minus 1 squared plus y squared equals 1. So that's 1/2 minus 1 squared. That's negative 1/2 squared minus y squared equals 1. And so this is going to be, that's a positive 1/4 minus y squared equals 1. See. All right, so solving for y, we will get y squared equals, I'm running into trouble again. 1 second. Let me see what I'm doing wrong. All right, I see it now. I see it now. It is just a silly transcription error. The equation 3 is not x minus 1 squared minus y squared. It's x minus 1 squared plus y squared. Right, so over here, this is a plus, which is what it should be. But along the way, I lost that plus and I got a minus here. So that is not what you want. Somehow we've been making a ton of small algebra mistakes, hopefully highlighting that this can absolutely happen. We just have to go slowly. And then when we recognize a mistake, we have to go back and see if we can fix it. So this plus, I'll point out, again, thankfully, it actually didn't affect us here because y was 0. So minus 0 squared plus 0 squared, it doesn't matter. Yeah. It did not affect our original answers. So our boxed numbers so far have dodged 2 bullets, which is great. Let's keep going and see what we can do down here. So equation 3 should actually give us a plus sign here and a plus sign here. All right, and thank goodness, I was also getting an error there where y squared was equal to a negative number, and I knew that was not the case. So now, that y squared is positive, we can actually proceed. So y squared will now equal 1 minus 1/4, so that's going to be 3/4, and we can get y equals plus or minus the square root of 3/4. All right, and I'm just going to rewrite that to make it look a little nicer as root 3 over 2. Not that we need to do that, but this has all been so messy at this point, might as well make it a little bit prettier. All right, so what does that give us? Oh my gosh, well, when the dust settles, and assuming we haven't made any more silly mistakes, we are going to get x value was 1/2, y value was plus or minus root 3 over 2, and so we're going to get 2 more solutions here. 1/2, comma, root 3 over 2, and 1/2, comma, negative root 3 over 2 as possible solutions. All right. And so that gives us 4 points of interest on our original curve that might be possible maxes or mins on the curve itself to the function f of x. I'll go back up and I'll mark those last 2 points, and those happen to be exactly the points that I kind of eyeballed earlier. So x is equal to 1/2 here, and y is equal to negative root 3 over 2, x equals 1/2, y is equal to positive root 3 over 2. So we would have to go in and examine all 4 of these points to identify which one is has the largest f value, that would be our maximum, and which one has the smallest f value, and that would be our minimum. All right, well, this was a monster of a video, complete with some really cool theory and some thorny computations and some minor but hopefully informative mistakes. So thank you so much for watching, and see you next time.